If you like power,
I get to light my own supernova.
the known universe has your fix.
God!
We're sizing up the ultimate stars in the cosmos. From our own sun
Think it'll break off?
It's getting there.
Oh, yeah. There it goes.
to ones even bigger and badder. Some come with mighty magnetic fields.
Go, girl.
Others release the brightest blasts known to exist. Grab a front row seat to see the universe's most powerful stars. To find out how powerful stars can get, we're on a mission to find the biggest, the most intimidating, the most awesome ones out there. But what exactly is a star?
Stars start off as big gas clouds. Gravity pulls those gas clouds together, and it gets so concentrated that you can start fusion in the core of what has now become a star. So stars are just basically giant balls of energy that are powered by gravity.
To begin our search for the best and brightest, there's only one logical place to start. The stellar dynamo that powers life as we know it. The sun.
There's a truly insane amount of power coming out of the sun. If you took every human being on the planet and let them explode the world's most powerful nuclear weapon like once a second, you still wouldn't have as much power as in the sun.
We're talking about temperatures which are way above any temperature we've ever experienced. The internal temperature of the sun is way over 1 million degrees.
But just how potent is all that power? In Huntsville, Alabama, at the Marshall Space Flight Center, NASA has a device that focuses intense sunlight onto various materials to see how well they can withstand scorching solar blasts. And theoretical physicist David Kaplan is about to see just how hot it gets.
This disk is a solar furnace. It takes the sun's rays and it focuses it into a single point. Back here, we have a reflector. The reflector will reflect the light of the sun into the solar furnace so we can heat things to incredible temperatures. The sun's heat that's concentrated in this little 3-inch diameter circle is about 1 megawatt per square meter. That's like being 3 million miles from the sun, and we're 93 million miles from the sun right now.
NASA uses this device to test heat shields for spacecraft.
What kind of temperatures can you get down there?
You can get a few thousand degrees. If there's enough heat going in and not a lot of heat coming off, it leads to meltdown.
If the sun can actually create a meltdown, David wants to see it. So he's putting various objects underneath what's essentially a giant magnifying glass.
All right, let's take this laptop and put it in the target chamber. I think we use computers a little too much, don't you?
Okay, I think we're ready.
This is going to be good.
To get this giant furnace cooking, there's no light switch, just a 2-story door. Open it and turn on the sun.
Ooh, I smell burning plastic.
It's on target.
Whoa!
It's heating up.
Yeah, it's on fire now.
I think that's good. All right, door closed.
All right. Oh, let's take a look. It smells bad. There we go. Hits the screen. The focus energy of the sun has now destroyed our nice household device.
In less than 10 seconds, the plastic laptop's shell reached its limit, igniting at just a few hundred degrees Fahrenheit.
Right in top.
But what if David kicks things up a notch?
Next thing we're going to try is this aluminum plate. There it goes. You see that? Oh, it's just turning to liquid.
Molten aluminum.
Ooh, I can even smell it from here. All right.
Woo!
Aluminum doesn't smell good when it burns. Ah! It's hot. Ow!
Aluminum needs over 1,200 degrees Fahrenheit to liquefy. And it got there. Time to test the sun with something stronger, like a steel meat cleaver.
This is about 1/4 inch thick of hardened stainless steel. We're going to put it in the target.
To melt steel, this solar beam will have to reach over 2,500 degrees Fahrenheit.
It's glowing. Oh yeah, okay. Yeah, it pierced a hole there. You think it'll break off?
It's getting there.
Oh yeah, there it goes.
All right, cut in half.
Oh boy, look at that. I don't know if it's still hot.
Whoo!
This turned to ash. That's amazing.
Pretty strong beam, I would say.
That thing's dead. Well, we destroyed this thing pretty well. We saw 3 different materials, and we got the sense of the sun, when focused, it transfers an enormous amount of heat, and it can basically destroy everything we've tried.
Where does all this power come from? It starts in the center of the sun, its core. Here, our star is eating through its main fuel source, hydrogen.
Our sun is burning hydrogen and fusing it into helium. Fusion is how stars support themselves against gravity. You've got gravity trying to crush the star down, but then the heat of all this hot gas is pushing the star back out.
But what would happen if even a small portion of that heat was unleashed here on Earth? If we opened up the sun and took out a chunk of the core, a 25 million degree piece, just the size of a small suitcase, it would obliterate a major city like Los Angeles from the inside out. First, it would superheat the surrounding air. This would then cause a fireball and shockwave that destroys everything, even buildings, for several miles. Finally, the high temperatures and flying debris cause nearly everything beyond the blast zone to catch fire. The resulting destruction and firestorm would doom anyone within a 60-mile radius. In reality, the sun would never hurl a piece of its core at a major city. But that doesn't mean it's a peaceful star. The sun still launches powerful assaults all the time, in the form of solar flares. And when it does, the sun becomes a fire-breathing dragon.
Solar flares are fascinating. It's one of the disturbances on the sun that creates this ejection of electrons and protons that can actually reach the surface of the Earth.
When a solar flare snaps off the sun, its radiation travels to Earth at over 180,000 miles per second. And plumes of charged particles can follow within a couple of days. They're so powerful, they can knock satellites off their orbits and cripple major electrical grids on Earth. One famous example occurred in 1989, when a solar flare knocked out electricity in the entire Canadian province of Quebec. What gives these powerful bursts their muscle?
Let's try this one here.
That's a mystery many scientists wish they had the answers to. But at Caltech, physicist Paul Bellin has an unusual way of understanding their strength. He's creating solar flares in his lab.
So what we're doing is setting up conditions in the lab that are analogous to what's going on in the sun. On the surface of the sun, there are magnetic fields that are like big McDonald's arches. And every once in a while they blow up, and that's what we call a solar flare.
Why these arches blow up to create solar flares is the unanswered question. But through his research, Bellin may have found the cause. When an arch forms, it has a tendency to twist.
What we think is happening is that it's getting more twisted, and then when it gets to a certain point where it can't handle it anymore, it breaks. and you get energized particles coming off. It's like an explosion.
To bring this type of solar flare to life, Bellin and his team use electromagnetism to ignite hydrogen gas inside a large vacuum chamber.
So we introduce the gas, we introduce the magnetic fields, and this all happens in a millisecond time scale.
What camera shutter speed are you using now, and how many frames per second?
4 million frames a second.
These astonishingly high speeds are necessary. Even at 4 million frames per second, this camera will only capture 14 frames of the flare. If everything goes as planned, the hydrogen gas will explode in the blink of an eye, creating a virtual solar flare that will live for just 1/300,000th of a second.
Let's go for it.
All right.
It looks like it's maybe extending beyond the original electrodes. We do see evidence of twisting here, and there are forces that are making this thing get bigger all the time. This sort of behavior was not predicted on the sun, but we clearly see that in our experiments.
Bellin and his team may be close to deciphering the power of solar flares here on Earth. But the true potential of our star can't be measured from 93 million miles away. It has to be seen up close and personal. And if we thought we'd seen the sun's raging power here on Earth, getting next to it may be truly mind-blowing. We've studied the power of our sun from afar. But to truly understand its strength, we've got to study it in its own backyard.
NASA's designed this mission called Solar Probe Plus to basically study the sun and something called the solar wind, which is this high ejection of solar particles off the surface of the sun.
But trying to get closer to the solar wind raises an important question. Can a man-made spacecraft actually survive a mission to a star?
NASA is looking at sending a probe toward the sun to explore what it's like in the proximity of the sun. Of course, the thing you got to worry about is getting too hot.
After watching the sun rip through steel like a buzzsaw, David Kaplan wants to know just how well NASA's Solar Probe Plus is going to hold up. To find out, he's heading to the Johns Hopkins Applied Physics Lab in Maryland, where engineers are putting their ideas to the test.
How close does a solar probe have to get to the sun?
Solar probe will get within 4 million miles of the sun.
So we're deep into Mercury's orbit.
Deep inside Mercury's orbit.
How do you protect the craft?
Well, the first thing is the thermal protection shield. That's the big plate that's in the front, made of carbon-carbon foam with some carbon composites around it. And on top of that is ceramic surface, and that both reflects some of the light and also absorbs some of the heat and radiates it out the sides of the spacecraft. And the front face of our thermal protection system is going to be about 1,700 degrees Celsius.
So about 2,700 degrees Fahrenheit.
That's exactly right.
What type of materials are needed to survive these temperatures? Time for a little solar barbecue.
I can cook this hot dog in my hand. The hot dogs are getting cooked, but my hand is perfectly fine. That's because this glove is made of material that can protect my hand up to 1,000 degrees Fahrenheit. What I'm interested in are the materials that can protect the solar probe very close to the sun in those extreme environments. I'm also interested to see what happens to this glove in those environments. Let's go take a look.
David's taking a piece of this heat-resistant glove.
Hey, I got a finger.
To go head-to-head with a piece of the special carbon foam that is supposed to shield the solar probe.
So we put a piece of the glove into the furnace, and we're going to take the furnace up to 2,500 degrees. And in here, we're going to find out if it can really handle temperatures that you get to when you're only a few million miles from the sun. We also have a piece of the heat shield that they use for the solar probe, and we're going to see how that fares too.
The only question is, which will win?
We're at 2,500 degrees. Oh yeah, it's glowing red hot in there.
It's back down to temperature. We're ready to open.
Let's take a look.
All right.
Holy cow. Look at that thing. Oh, yeah. Oh, that's a shell of what it once was. Now, that thing is disintegrated.
Melted the plastic and everything.
It really is charcoal. You could barbecue with this stuff.
But the heat shield is intact.
That's incredible. These two materials just experience the same heat. This glove, or what's left of it, could get up to 1,000 degrees, but at 2,500, we see what it turns into. But this material, nothing happened to it, except maybe a little charring that came from the glove itself. This is the stuff that's going to protect these devices from the incredible heat a few million miles from the sun.
Okay, so the shield can take the heat. But will it protect what's inside the probe?
We just did this test and saw that this shield material could withstand 2,500 degrees. And my real question is, can it actually protect the thing that's behind it, the solar probe?
Yes, I'm actually going to show you. Here we have our carbon material.
Wow, this is very light.
Yes, it's about 97% air.
I see. This is like holding styrofoam.
This lightweight foam is also used in jet engines, making it ideal for standing up to extraordinarily high heat.
So this is a thermocouple.
Okay.
So we can tell what the temperature is. And I'm going to get the front surface hot, and I'm going to dare you to touch the back surface.
Okay.
If you don't trust me that it's going to work,
yeah,
you can actually see the temperature.
Just watch the monitor,
yeah.
Okay. So I should put my hand back here now?
Yep. I'm going to get the front surface.
Is it glowing yet?
It is glowing.
Okay.
Your hand's been back there. It's been glowing for quite a while.
The side of the shield that will be exposed to the sun is climbing over 2,000 degrees Fahrenheit. But on the other side, David's hand is only feeling about 130 degrees.
It's amazing because one side of the material is extraordinarily hot and the other side is just
really
cold even.
Yeah, yeah.
That's a big deal. Huge swings in temperature can be devastating.
If you take, like a glass out of the dishwasher, it's super hot, you put cold water in it, it can shatter.
It can shatter, exactly.
So here too, there's going to be very hot surface, a very cold surface.
Right.
It's 132 degrees.
Mm-hmm. It's about what it gets
Which is a far cry from 1,781 degrees.
Solar Probe Plus is out to conquer the intense heat of the sun, but what it's designed to study may prove to be far more potent: the solar wind.
The sun emits what's called a solar wind, tenuous particles streaming out from the outer parts of the corona. And basically, it fills our solar system. The bubble of solar wind that permeates our solar system is called the heliosphere.
The edge of the heliosphere proves that the true power of our sun isn't found on its surface. It extends way out past Pluto. As the solar wind bursts out of the sun's atmosphere, it whips past the Earth at 1,000,000 miles an hour and blows by Saturn and the outer planets in just a few months. Near the edge of the solar system, billions of miles from the sun, the solar wind slows down abruptly. This point is called the termination shock. Here, the wind is colliding with matter from outside the heliosphere, becoming denser and hotter. And as this phenomenon continues beyond the shock, it creates a scorching layer of hydrogen gas. Far from any star, yet unbelievably hot and powerfully charged. But what causes the temperature to spike? Astronaut Mike Massimino and scientist Steve Jacobs are about to unleash a 250-gallon shower on this platform to see.
All right, Jake, where are we here? What is this thing?
This is an excellent model of the heliosphere.
The heliosphere.
And there's interesting phenomena that occurs at the edge.
What do we expect to see here, Jake?
We're going to drop water down on here, and it's going to spread out.
Okay.
The way water acts when it hits the plexiglass is similar to what happens as solar wind spreads throughout the solar system.
It starts to build up, it interacts with the plexiglass and makes a little wave, a sheath, a circle, and we'll see it.
All right, how do we get this thing to work?
I gave you that magic box.
That's what this thing is for? Are we going to be dry down here?
Let's find out.
All right, here we go.
For it.
Armed and fire. at that. What are we looking at here, Jake?
Well, that dot represents the sun.
That's the sun right there.
The water transferring out, that represents the solar wind, and the particles inside that wind are traveling 700,000 to 1 million miles an hour. And they start to slow down out here, and when they interact with charged particles out there, they bunch up, slow down, and impact with them.
Okay, and that's where we see it getting red again.
And that represents the shock right here where they bump into each other.
Yeah. And how hot is it getting around here?
200,000 degrees. It actually heats up there.
Well, that's kind of almost counterintuitive that as you're close to the sun, you expect it to be hot.
Right.
And as you get further away, the zone out there warms up again. Why is it so hot there?
Well, the same phenomena that happens in the sun when particles are forced to interact and rub together. You know, they will emit radiation in the form of light, which we see, and heat.
And heat, kind of like friction.
Like friction, kind of like friction, yeah, friction.
It's interacting.
Yeah, interacting. A neat model, right?
It's cool, but we're just looking at this right over our head. It's a representation of our solar system, and we're getting to look at it
right here.
Right here.
The power of our sun is truly amazing, stretching far beyond any planet. But it's not even close to being the biggest star in the universe. For a truly spectacular headliner, you want size. The largest star that we know of is VY Canis Majoris. It's what's called a red hypergiant. And it's 4,900 light years from Earth, and better known by its pet name, the Big Dog. But can stars actually grow to enormous sizes?
In the early universe, there was only hydrogen and helium. That's all that was created in the Big Bang. Since there weren't any heavier elements in the early universe, that allowed stars to grow really huge, 300 times the mass of the sun, or maybe even 1,000 times the mass of the sun. They could get to be huge, fat beasts.
Those early stars aren't around anymore, but the Big Dog is, and it's estimated to be 2,000 times the size of our sun. Just imagine our own star growing to the size of Canis Majoris. It would immediately swallow Mercury like a bite-sized appetizer. Then pulverize Venus. It would bake the Earth like a pizza and vaporize our watery planet. Mars would be an instant goner. And finally, it would devour giant Jupiter like a pea. With a radius near 880 million miles, the Big Dog would eat every planet until it nipped at Saturn's heels. Fortunately for us, Canis Majoris is in a distant part of the Milky Way, far enough away to stay in its own backyard. But when it comes to pure power, size doesn't always matter. There are stars out in the universe that can make the Big Dog yelp like a chihuahua.
Another way we classify stars is by their power or luminosity, or like the wattage of a light bulb. There are 100-watt light bulbs, there are 10-watt light bulbs, there are 1,000-watt light bulbs. Those are different powers, and in a similar way, stars can have different powers. The bluer stars are hotter, the redder stars are cooler.
So how much more power is in a blue star than a red one? In the constellation Orion, a star named Rigel, a blue supergiant, shows it pretty clearly. It's not as large as the Big Dog, but if we swapped it with our sun, it would still extend out to Mercury. You'd think we'd be okay, but size isn't what matters here. Rigel's powerful radiation would boil away our oceans and then snuff out Earth entirely, leaving nothing but solar dust. Rigel would also fry Jupiter, dissolve its moons, and even destroy the rings of Saturn, which would melt like ice cubes in a hot oven. Rigel then bakes all the gas giants, and could leave them looking like massive comets with spectacular tails, all destined to vanish. But even with all its incredible power, Rigel still isn't the king of the stellar forest. There's another beast in the universe.
The most massive star known is a star called R136A1. It's almost 300 times the mass of the Sun, which is really huge.
Located in the Tarantula Nebula, R136A1 is 165,000 light-years from Earth. And we can still see it, which tells us how truly powerful it is.
R136A1 is a very, very special star. Most stars never get up to such a high mass because they're so powerful that the radiation just blows the star apart. Back when the universe was very young, there hadn't been much chemical processing. Very massive stars, having hundreds of times the mass of our Sun, were probably much more common than they are now.
R136A1 is a blue hypergiant, the highest class of star in both power and size. And on top of that, it's rapidly shedding mass, becoming extraordinarily bright. It's the total package when it comes to stars.
Finding R136A1 is kind of like finding one of our fossil ancestors. It's a glimpse into what stars used to be like.
The incredible heat generated by massive stars such as Rigel is due to another muscular force in the universe: pressure. Every star is under intense pressure because of their extreme gravity and density. That pressure creates incredible heat. And that fuels solar fusion, which powers the star. So how does pressure create heat? Aerospace engineer Sigrid Close has a device to show just how easy it is.
So a lot of people think that the bigger a star is, the more likely it is to create fusion inside. It's actually not true. It's all about the pressure and the temperature. You need a high enough temperature to overcome something called the Coulomb barrier. Basically, particles don't like to get near each other. If you have like particles, they want to stay away from each other. The key is pressure and temperature. So you have enough of it, then you can overcome that Coulomb barrier and actually create fusion.
Pressure creates intense heat in the most powerful stars. But the hardest hitting force in the universe isn't a living, fire-breathing star. It may be a dead one. The size of the big dog and the heat of Rigel are about to be blown away by the violence of another monster in the universe. This may be the most frightening sight in the universe. It's the death of a star. A supernova.
All massive stars are ticking time bombs. They are going to blow up sooner or later. Usually they only have a few million years to maybe 100 million years. The thing that makes a supernova so powerful is gravity. You get burning of nuclear fuel that props the thing up against collapse due to gravity. But when you run out of fuel, the whole thing collapses and you can smash stuff together and you get a big explosion.
At Princeton University, astrophysicist Adam Burrows is creating some of the first ever 3D simulations of this explosive process. A phenomenon that lasts just half a second.
Nature is three-dimensional, and so now we have access to, by dint of better codes and better computers, the full phenomenon.
These supercomputers allow Burrows to estimate the energy inside the core of a supernova using the mathematical values of fluids in motion. And he gets surprising results.
The velocities are on the order of maybe 50,000 kilometers per second. The accelerations are on the order of 1 trillion Gs. The velocities are very large, the energies are very large, and the phenomenon is very violent.
With these numbers, Burrows can now create pioneering simulations of the turbulent tidal wave of gases exploding deep within the belly of the beast.
We are looking at the first example of a 3D simulation. What we see here is an explosion, but the explosion is very broken up and asymmetrical. It did not maintain its sphericity. And in the 3 dimensions that we now enable, it's completely fractured and broken up and unstable.
Realizing these explosions aren't uniform is important, because when a supernova blows, it sends out material that has a big effect.
If they're close to us, when they go off, they will cause significant damage. Life on Earth may be very difficult and problematic after a supernova. It would be a very, very bad day.
But it's one thing to run computer simulations in a lab. How can we see this effect in real life? Can we recreate the asymmetry of a supernova explosion here on Earth? Astronomer Andy Howell is about to find out by igniting some gas-filled balloons.
So there's a lot we don't understand about supernova. We know the aspherical nature of the explosion is part of what makes them go boom. I want to see if we can get that aspherical nature in this kind of explosion. So we're building a 6-foot acetylene bomb here. We've got this net set up so that people don't have to be there when we blow it up. We've got this remote filling system. We've got some fire extinguishers, a remote detonation system set up.
Balloon filled, high-speed camera in place, showtime. But to get the powerful death blast of a star right, this has to be a monster bang.
All right, here we go. I get to light my own supernova.
Oh my God, dude!
Man, that was a bang! Damn! That was so fast, it was just unbelievable. It scared the hell out of everybody. Oh, wow. I felt the explosion. It really felt like I got the kicked out of me. That was really like a supernova.
Now for the instant replay. Shot by a high-speed camera at 20,000 frames per second.
Let's see what it got. Oh, that is cool. That looks a lot like a supernova. I mean, it actually looks better than a supernova in a lot of ways. In a supernova, we just see this distant point of light, and we can't really resolve all the details. But here, we can see all these fast-moving bits that are just flying away. That's just like in a real supernova. We often get little blobs of calcium racing out 1/10 the speed of light. And you can see there's all these turbulent eddies where gas is turning over from these instabilities you have in the explosion. And this is exactly like what we see in the modern simulations of supernovae. In real life, things are really messy and turbulent and mixed up. We're just starting to be able to do on a computer what nature does when you blow something up.
So what does this tell us? Could the blast from an asymmetrical explosion in deep space reach the Earth?
You know, it's nice to admire them from afar, but if you got it really close, you know, these are big, giant explosions that are taking place out there in space, and you wouldn't want to get too close.
Today, astronomers are watching one particular star 8,000 light years away that could be a real threat to Earth.
Eta Car is a really massive star that's pretty close by. When that thing blows up, it's going to be a big spectacle. It could have blown up already, and the energy could be headed towards us.
Light and energy from Eta Carinae takes 8,000 years to reach Earth. So if this star has already gone supernova, it could be sending high-energy radiation called gamma rays right at us. If this burst hits Earth, it could wipe out up to half of the ozone layer. Almost all living things would die within hours. And then the planet could cool so rapidly it would trigger a new ice age. Luckily, Eta Carinae's line of sight is tilted about 45 degrees off the path of Earth. So its deadly gamma-ray burst would be a near miss, and we dodge a bullet. But after a star kicks the bucket, what remains can rise from the dead and become a force to be reckoned with.
When a gigantic star collapses, the whole thing gets crushed together into nuclear densities. Everything is neutrons. Stuff that should not touch is all crammed together inside of a neutron star.
And a neutron star is basically the density of the nucleus of an atom. So it's very small for a star, but its gravity is stronger than any other star in the universe.
And in the world of neutron stars, there's one type with amazing power. It's called a magnetar.
A magnetar is a special type of neutron star that has a truly immense magnetic field. The strength of the magnetic field is about 1,000,000 billion times the strength of Earth's magnetic field at its surface.
But magnetic fields, how powerful can they really be? Aerospace engineer Sigrid Close and scientist Steve Jacobs are going to let one of Earth's strongest permanent magnets show magnetic fields are something we don't want to mess with.
What are we doing here today?
You mean you don't recognize this?
I don't know what this
They
is.
don't. This is our homemade magnetar demonstrator. Right down in between these two metal plates, I've got an aluminum plate and a steel plate, and in between is a very, very, very strong neodymium magnet that has the strength of about a Tesla.
So magnetars are about 10 to the 10 Tesla, so 10 billion times as strong as this.
But this magnet still has tremendous pull. In fact, it wants to slam into this steel plate, and the only thing holding it back is this chain.
I've got a strain gauge right here, and it's set on 0 right now. So I thought it would be fun to see what would happen to my hand if I left it in here and we disengage that chain.
I think it would hurt.
You think it might hurt?
I think a little bit.
Well, since I'm right-handed, I'm gonna use my left hand for this one, okay? What do you think? You know, it's great, isn't it? How do you do? I'll set the gauge on 0, and in a second, we're gonna disengage the safety chain, and I'm gonna put my hand right here, and I'm gonna have you push up.
You tell me when to go.
On your mark, get set, go. There it goes. Now let's watch that magnet. Oh. Aha! Oh, I'm stuck.
This powerful magnet isn't about to let go. So to overcome its immense force, it's going to take muscle. And lots of it.
Gentlemen, are you ready?
We're ready.
All right. At your will, go.
Okay, guys, on the count of 3. 1, 2, 3.
Come on, guys.
Not working.
It's not working. Don't hurt yourselves on my hands account. It's okay. You did a good job. You did your best. Thanks, guys. Sorry, but what can I say?
This magnet is unbelievably powerful. Again, only a billionth that of a magnetar, but it's still, we have not been able to free his hand.
But they got, what, near 1,000 pounds of pulling there.
Yeah, I think it was a little over 1,000.
A little over 1,000.
Human muscle isn't going to beat this magnet. But will it stand up to some Detroit muscle? The magnetic field of a powerful star called a magnetar can't be underestimated. To show the true power of these fields here on Earth, a super strong magnet is stuck on a steel plate, and it's not budging.
Gentlemen, are you ready?
5 muscle men couldn't pull it off.
Not working.
It's not working.
But what if we add a little horsepower?
Let's go see what happens.
All right.
Go, girl. There she went.
Yes!
You did good.
Horsepower works.
Look at the dial.
All right.
Look at that, 2,000 pounds.
Very cool, very cool.
You did a good job pulling.
Yeah.
That's a lot of horsepower, my lady. I'm telling you.
Thanks for the equal and opposite reaction.
So I guess that's what it was.
This is a 1 Tesla magnet. This is a billionth of what a magnetar can do.
We had a modest victory, didn't we?
Yeah, and I'm glad that wasn't.
And that would be me on a magnetar, right?
Right.
But even the strongest magnets on Earth can't hold a candle to a magnetar. Even though it's 180 times smaller than our own moon, just 12 miles in diameter. One of these stars is so powerful that if it came within 50,000 miles of us, its magnetic field would be 10 times more powerful than ours, wiping out every credit card on Earth, stopping compasses, even erasing your entire hard drive. And if it were even closer, just 600 miles away, the magnetar would be 5 million times stronger, sending anything metallic flying everywhere, and turning the atmosphere into a giant electrical storm, ripping atoms apart and leaving nothing intact. But none of this would even matter, because in the time it takes to hit a golf ball, the entire planet would be sucked into the magnetar, turning into a stream of plasma, leaving nothing but empty space behind. But if the force of a magnetar seems unbeatable, the universe has one last surprise. It's potentially the most colossal power around.
Sometimes when a star goes supernova, it's so massive that it doesn't even create a neutron star. Nothing can stop this thing from collapsing, and it collapses right down into a black hole.
But not all black holes are created equal. There are supermassive monsters out there, while others are surprisingly small.
Scientists have debated the hottest, most powerful spots in the universe, but one theory is that they're inside of micro black holes. These are black holes smaller than the tip of this pencil, even smaller than an atom in the tip of this pencil, smaller than the nucleus in that atom, and about the size of a proton. To get an idea of the temperature of these micro black holes, you have to add another 42 zeros to the sun's 15 billion degrees. These things are so hot and so powerful that they evaporate almost as soon as they're formed. They only last for an octillionth of a nanosecond.
Searching for the most powerful stars, the irony is something microscopic, something we'll never see, outshines them all. But as we continue to find new stars, bigger, more exciting possibilities await.
As an astronomer, I've really been surprised in the last few years with some of the incredible discoveries that have been made. As we get better telescopes, as we get faster computers, who knows what we'll find?